The shift from fossil fuels to electrification is transforming every corner of the economy. At the heart of this transition are high-voltage systems made up of batteries, cables and connectors that need to work seamlessly together. Today we are joined by Smiths Interconnect to understand where the real challenges are in making those systems reliable and how new technologies are trying to make a difference. So, Joydip, welcome. Given the need for high-voltage batteries, cables and connectors at the heart of energy transition and electrification, where do you think is the weakest link in a high-voltage electrical system?
Yes, it's a great question to start with, really, because if you really think this through, right, and I suppose I'll surprise many when I say the connectors, sadly, is one of the areas of weakest link within the DC power transmission architecture. Now, you might wonder why, right? It's if you really kind of zoom into a connector, and particularly the heart of the connector, which is a contact technology, you will find the pin in contact with the socket which is machined. And what looks like a naked eye, a perfectly smooth surface, actually is not smooth. It's got a lot of irregularities. And when you're transmitting DC power, you're actually transmitting across those irregular touch points. Now, what happens really in real life is across those irregular surfaces where you're transmitting the power, you create what's called a constriction current. Now, the constriction current, along with the contact resistance of the inherent material, creates localized heating of that environment. So if you really want to simplify the science and kind of make it short, really, is higher the contact resistance, higher will be the localized temperature rise, and therefore loss of power due to joules heating. So just think this through, right? As an engineer, one spends a lot of time sizing the batteries correctly, sizing the cable correctly, knowingly or unknowingly picking up a connector which has got a constricted path, limiting the amount of energy that can transfer from point A to point B. So yeah, that's the reason really, yeah.
So how can that power loss be addressed?
So you see, we as a business picked this pain point up because to our rather surprise, you'll find it's a staggering amount of energy loss happening with DC power transmission. So we spent a lot of time designing a technology called Hypertac Green Connect. This contact technology has been designed particularly for DC energy transmission, but particularly for applications that require what's called as a peak current, which basically means that, for example, it might be using a rated current of 300 amps, but momentarily it might be requiring 500 amps for 10 or 20 seconds. So what happens is, if you really try to kind of understand, and kind of from a technology standpoint as to how the user benefit from this is with a lot of other contact technologies out there in the market, you have got inherent high contact resistance. So when you're particularly trying to draw current at a peak current level, you don't have a lot of headroom. Because of the temperature rise, the curve is rather steep. With Hypertac Green Connect, the way it has been designed, it has got it was designed from a number of different lenses, if you like, from a design standpoint. So you've got material science. So we picked up materials that are inherently high conductive. That means it creates low contact resistance. Then you have got the hyperboloid contact technology itself, which means that it has got wires across the contact surface with the pin, therefore limiting the amount of temperature rise. And fundamentally, and the final aspect of that technology, which is, I suppose, not a lot of people do pay attention to, is the crimp area. We have developed a particular feature which further goes to reduce the contact resistance, to again reduce the temperature rise, because one of the peculiarity of the peak current area is, and this is a particular nuance in certain applications that perhaps we will go on to talk about, is when you need peak current, you need to have a lot of headroom, and therefore the temperature rise kind of curve has to be as shallow as practically possible, because alongside this, in this architecture, you've got the battery management system sitting next to it, which is closely watching the critical temperature. And as soon as it reaches that critical temperature, it starts derating the current. So in this peak current environment, the Hypertac Green Connect gives you a lot of headroom to allow power transmission to happen at an elevated current for as long as 20, 30 seconds, depending upon the environmental conditions along with it. So this is how I suppose we are really trying to solve a critical problem in applications that require a peak current, and also in applications that require thousands of meeting cycles, basically. Yeah.
And following on from that, so what applications actually benefit from this technology?
Yes, it's a great question, because you see, there are lots of end-use applications that today are benefiting from electrification, right? So electrification is a major mega trend that you see in a lot of different end segments. But what we have particularly done is we have, again, there are lots of good connectors out there in the market, right? Don't get me wrong. But there's a difference between good and great. Because what we see is that there are a lot of good connectors that have been what I call as repositioned to an adjacent market. So they were developed for, shall we say, energy storage market, static energy storage market, and they were repositioned to applications that require peak current. So we are particularly therefore designed this Hypertac Green Connect. But coming back to your question, so we are particularly looking into DC power transmission that requires this peak current in harsh and arduous environment. For example, in aerospace and defense applications, like these days there's a lot of development happening with eVTOL, right, or land vehicles. Then you've got another area in the industrial market like mining. There's a mega trend around electrification of mining. And finally, also railway applications as well. So across the board, there are a lot of different applications, but we have really zeroed into a particular segment of that market that requires DC transmission, but DC transmission along with the need for peak current requirements. Yeah.
Okay. Are you excited about the future with how this is going forward?
Oh, absolutely. It means, we see so many different customers organizations working in this particular application. But I come back to this point that, it's the fundamental part here is when so much care has been taken in designing the subsystem, it's a shame in a way that a connector can let down an overall optimal system working in the best power transmission possible, really. Yeah.
Okay, thank you. I think that's all we've got time for. Thank you for joining us.
Thank you for having me.
And thank you for watching.